All right, today we're going to talk about something really cool in machine learning, a concept that kind of pulls back the curtain on a lot of different predictive models. We're talking about generalized linear models, or GLMs.
So just think about this for a second. If you want to predict something like a house price, it feels pretty straightforward, right? You've got data, you can pretty much draw a line through it. But what if you need to predict something that's just a yes or a no? Like, is this email spam or not? You can't just draw a straight line for that. It's a whole different ballgame.
And you can see the problem right here. On the left, you've got your classic linear regression. That straight line can just keep going up and up, which is awesome for something like a price. But look at the right. For a yes or no situation, what we really need is a probability, a number between 0 and 1. A straight line just completely breaks down here. We need a totally different shape, like this S-curve that you see for logistic regression.
I mean, they look like two totally separate things, don't they? A straight line versus this curvy S shape. But what if I told you they're not separate at all? What if they're actually secretly part of the same family? That's the big idea we're going to unpack.
To really get this, we've got to take a step back and realize that prediction problems themselves come in all sorts of flavors. It's not always about finding a number. The thing you're trying to predict, your target variable, it can be a continuous number, like a price. Or it could be a binary choice, pass or fail, spam or not spam. Or it could even be a count, like the number of people who visit a website in an hour. And that number can't be negative, right? You can see how one rigid model would really struggle to handle all of these different scenarios. And this is where the solution comes in. And it's so elegant. Instead of having to learn a dozen totally different models from scratch, what if you could just learn one single, super flexible framework that can adapt to all of them? Well, that framework is the generalized linear model. Here's the perfect way to think about it. A GLM isn't really one specific model. It's more like a family name. And models you probably already know, like linear regression and logistic regression, they're just famous members of this really big, really versatile family. And check this out. Here's the family tree itself. You see generalized linear model sitting right there at the top. It's like the common ancestor for everything else. And branching off from it, you see all these different paths for different kinds of data, which then lead to the specific models we end up using, like logistic or Poisson regression. So how in the world does one single framework do all of this? Well, the secret is that every single GLM, no matter what it's for, is built from the same 3 simple parts.
Okay, let's break it down. It's actually super simple. First, you have your input data. No surprises there. Second, at its heart, every GLM does a simple straight line calculation, just like you would in basic linear regression. But then, and this is the magic trick, it takes the output of that line and runs it through a third component, a special shaping function.
This shaping function is the absolute key to everything. Its job is to take that raw output from the straight line part, which could be any number, positive or negative, and it bends it, or squeezes it, or transforms it into exactly the right shape for the answer we need, whether that's a probability between 0 and 1, or a count that has to be positive.
Just look at this example. This curve is an exponential function. If you take the result from that linear model and feed it through this curve, the final prediction is guaranteed to always be positive. No more negative predictions for things that can't be negative. This is perfect for predicting counts or rates. The linear part does the heavy lifting, and this shaping function makes sure the answer actually makes sense.
So now you can see how this works. By just swapping out that shaping function and making a few different assumptions about our data, we can create this whole family of specialized models. And here they are, some of the stars of the GLM family. You've got your linear and logistic regression, of course, but you also have Poisson regression for counts and a bunch of others. They all share that same simple linear core, but they're each specialized for a different job. This table really spells it out for us. If you're predicting continuous numbers like a house price, you use linear regression. If you've got a yes or no problem, like finding spam, you grab logistic regression. And if you're predicting counts, like how many calls a call center might get in the next hour, you'd use Poisson regression. It's the same family, just different specializations for different jobs. Honestly, the best way to think about it is like a toolbox. The GLM framework is the box itself. And once you understand how it works, learning a new model isn't like starting over. It's just like grabbing a new tool. You already know how the handle works. That's the linear part. Then for each new job, you just snap on the right head. A screwdriver for one thing, a hammer for another. That's your shaping function.
Okay, so why does this all matter? Why is this such an important concept to get your head around? Because it's more than just a cool academic idea. It actually changes how you look at the whole field of machine learning.
The real power here is that GLMs give us a unified theory. So instead of trying to memorize a dozen different disconnected models, you just learn one flexible system. And this doesn't just make things easier to understand, it reveals these deep, fundamental connections between algorithms that, on the surface, looked completely different from each other. And that kind of leaves us with a final question to think about. If these foundational models that we use every single day are all just variations on one single theme, what else out there in the huge, complicated world of AI is way more connected than we think? Makes you wonder, doesn't it? Thanks for tuning in.